This is problem 9-70E. It's on page 519. The directions for this are generic. There's several different problems. It says use the superposition method to determine the reactions at all supports. Draw complete shearing force and bending moment diagrams. Indicate the maximum shearing force and bending moment for each beam. Now, the beam itself looks like this. It's a cantilever beam attached to the wall, or to a wall. It has a reaction out at the end. This is what makes it statically indeterminate. So there's a reaction at D. The wall is labeled A. Bless you. 3 feet out, there is a 1,200-pound point load. There's a distributed load along the entire length of the beam. And seems like we had noticed that they didn't have a load on it. I looked it up, and it was supposed to be a 400-pound force per foot load. So if any of you have a printing that has the corrected figure, then you'll know the value, and it'll be the same. I think we had decided last time on some random load, but this is the one that I'll use since it was the intended load. So anyway, moving along, there's another point load of 800 pounds force out at 3 more feet, and then there's 4 more feet to get to the end of the beam. Obviously, there's going to be a reaction at A as well as a moment at A. Now, in order to solve this, what I'm going to do is start off trying to get the reactions at A and D. And to do that, what I'm going to do is look at this as if it's the sum of several different beams that are loaded in simple ways. So for example, the first beam will simply be a beam that has all of the distributed load on it. So this 400 pound per foot load is one load. So let's continue. The next one will be, I'll take that to be the 1,200 pound point load. Then the 800 pound point load. And really the reaction out at A is another point load. We don't know it, I'm sorry, D. The reaction at D is another point load. We don't know its magnitude yet, but we should be able to find it. So I'm basically breaking down the loads into 4 parts. And like I said last time, we're going to superimpose. We're just going to add them together to get the solution. Now, here's the basic idea. If we call this 1, 2, 3, 4, we could calculate the deflection out at the end, right, from each of these loads, or at least come up with an equation in the case where we don't know RD, that represents the amount of deflection out at the end of a beam that's loaded this way. It's pretty simple, right? All we have to do is go to the back of the book and what is it, Appendix 25, I think? Appendix 25 are the statically indeterminate beams. And just select the appropriate case that matches what we've got here and perform our calculations. Actually, it's 24. 24 is the one that has just simple loads for cantilever beams. So basically, what we're going to do is take a statically indeterminate beam and make it essentially statically determinate. Okay? So we could actually solve for the deflection out here, or we could solve for the reactions and things. But what we're going to do is say, well, if we add the deflection, we have to get 0, because we know that out at the end, this endpoint can't move. There's a reaction here. That reaction will be whatever magnitude is necessary to prevent the end from deflecting. Does that make sense? So we're going to represent the deflection as a function of each of these loads, add them together, and then realize this load is going to be whatever it needs to be to force this to 0. Does that make sense? That's going to be our strategy. So let's see if we can find what the deflection would be if this was the only load. So page 737. What case does this first one look like? It looks like C, that's right. On page 737, case C is just a distributed load. And where am I holding the book? because I didn't write down the case letters, that's why. Anyway, so the deflection out at the end, out at D, so these are all gonna be at D. The deflection for case one is just negative WL cubed divided by 8EI. Okay, what is that? Well, this is the lowercase w, so it's the distributed load, so negative 400 pounds force per foot, multiplied by the length of the beam, which is 10 feet, has to be cubed by the equation over 8EI. Notice we don't know what material the beam is made of. We also don't know what the beam cross-section is like. So we don't know what E and I are, but we can write this, we just plug these numbers into our calculator, we can write it in terms of E and I as follows. So there'd be 50,000. What units would I end up with here? In the numerator at least. Almost. We got pounds per foot times foot cubed.
So it would be, sorry, pounds foot squared.
Good. Pounds, feet squared in the numerator. And now I've factored the 8 in, so I just have over EI in the denominator. Okay, so there's the first case. Now looks like I'm gonna end up running downhill a little bit. So the next case, what does that look like? In fact, the last three cases all look the same. They're just point loads, right? So what do they look like? Essentially B, right? At least the next two. 4, we'll use case A because case A has a load out at the end of the beam. Okay? So we're going to use case, what did I say, B? Yeah, case B for these two since the load P is not out at the end, and then case A for this one. So if you look at the equation for the deflection out at the end, you'll see that for this case, it's negative P A squared divided by 6EI. Okay. So negative P, well, that's just the negative 1,200 pound force load. A is the distance from the support at the wall to the load, so that's just 3 feet.
Don't you also have to multiply that by 3L minus A?
Oh, thank you. Yeah. Didn't finish copying my notes before I started plugging in numbers. You're right, thank you. 3L minus A. So let's see, here we go. 1,200 pounds force. I hope I don't run too far off the video here. A, again, is 3 feet. It has to be squared, divided by 6EI. And this will be 3 feet times L, which is 10 feet. Or 3 times 10 feet, minus A, and A again is this distance here, okay? So that's just 3 feet, okay? Let's see, I expect to get the same units. What am I doing wrong? No, that's, yes. Oh, okay. I expected to get pounds force feet. It looks like I'm gonna get pounds force feet cubed. I have to get the same units. Hang on, we'll figure it out. Well, I just noticed that this doesn't make sense. Let's continue with the problem, and I'll figure out what I'm doing wrong with the units, because the units are bothering me. There's no way that's right. So deflection doesn't make any sense, unless there's a misprint in the book.
Yeah, your capital W is the total load, which is the distributed load times the length. So
Yeah, I realize that, but I don't think they were using capital W. They were using capital W. You're right, thank you. So I've made a mistake in my solution. That means I will need you guys to give me a hand here. Let's see. Yeah, see? You should always check your units. I didn't check my units, that's what went wrong. Or at least I thought I did. I actually have units written here, and I just wrote the wrong thing. You're right, this should be capital W. I was using the wrong thing. So 400 pounds per foot times 10 feet, that's gonna be 4,000 pounds force of load. Okay, so that should mean that I need to add another 0 here. Does that look right? because all I've really done is multiplied by 10. And now we have units of pounds cubic feet. There we go. All right, so I'll need calculator help along the way because my numbers are going to be wrong here. So Y2, let's see, what would we have there? Well, we've got 3 times 10 is 30, minus 3 is 27. Anyway, plug all the numbers, the 1200, the 3, the 27, and the 6 in your calculator. You should find that this one's negative 48,600 pound force feet cubed over EI. Okay? Y3 will look just like this one, right? So rather than writing the equation down again, I'll just plug in the numbers. It would be negative 800 pound force for load P multiplied by A. Now you have to be careful. A is a different number for this case. A in this case is 6 feet because the 800 pound load is over at 6 feet from the wall. So let's see, A 6 feet squared times 3. L is the length of the beam still, so that's 10 feet minus A. This time instead of before, A was 3 feet, now A is 6 feet. Okay, let's see, that takes care of the numerator over 6 EI. And plug all of that in your calculator, the 800, the 6 squared, the 30 minus 6, 24 over 6. Plug all that in your calculator, you should get negative 115,200, so 115,200 pound force cubic feet over EI. And then now finally for this last one, we could use the equation that we've been using so far. We could use this equation, but there's no point in doing that. It's overly complicated for this case. And so instead we'll use case A, which has the load out at the end. You have to be a little bit careful here because the equation is negative P L cubed over 3 EI. Okay, so when the load is acting downward, then we leave the negative sign, but since the load is acting upward now, we'll end up with a positive sign. So in a way, this is a negative load and that's a positive load. Does that make sense? It's kind of strange, but that's the way it works out. So P is going to be R sub D, that's the reaction at D, multiplied by 10 feet cubed for L cubed over 3 EI. So this is going to come out to 333.3 repeated, R sub D over EI. Okay? So that's the deflection at D from each of these cases. Like I said, when we add them up, we should get 0. So let's see. Let me put them right here, I guess. So Y1 plus Y2 plus Y3 plus Y4 have to give us 0. So that would be negative 500,000. And then minus 48,600. It's 40,600 minus 115,200. Okay, plus 333.3 repeating RD over EI. Now all of this has to come up to 0. So do you see that the EI don't matter, or doesn't matter? We can cancel it out by multiplying through by EI. And this is equation then, this is an equation that would allow us to solve for RD. So RD would be equal to, let's see, 500,000 plus 48,600 plus 115,200 divided by 333.3 repeating. Okay, that should be R sub D. So put that in your calculator, please, because I put 50,000 in my calculator when I did this before, and I've got the wrong answer.
1,991.6.
1,191.6 pounds force?
1,991.
1,991, okay. Anyone second that? Okay, all right, so there's our reaction at D. Okay, how about the reaction at A at the moment? Well, now we can actually compute this, right? Now it's not too bad because we can simply sum forces in the y direction and come up with the reaction at A. So let's do that next. In fact, really all of this work was just to get the reaction at D. There's nothing else of any particular value here, so let's get rid of this. We need the space. And so summing forces in the y direction, we should get 0. And so that would be the reaction at A. In fact, here, let's just do it this way. So this implies that the reaction at A would be equal to, let's see, 4,000 pounds force for the distributed load, plus 1,200 pounds force for the first point load, plus 800 pounds force for the second point load, minus the reaction at D. Okay? So the reaction at A has to support all of the loads except for what RA supports. Okay, so what do we get for our reaction at A then when we do this? It's gonna be 4,000 something, 4,000.
4,084.
How much?
4,008.4.
4,008.4?
Yeah.
Okay. All right, that makes sense. So there's the reaction at A. Now what about the moment at A? Well, for that we just sum moments. About A. You guys are statics experts, correct? Right? Okay, good. Okay, so tell me what to write down here for this sum of moments about A. MA, good. Why MA? Because MA is an externally applied moment, right? And then what else?
1,200 times the.
Plus or minus?
Minus.
Minus. 1,200 pounds force times what moment arm? 3 feet, good. Okay. In the same vein, 800 pounds force times 6 feet. Plus 1991.6 pounds force, the reaction at D multiplied by 10 feet, good. What else? How about if we just do this? Can't we say 4,000 in the middle? Okay, let's just do that. So minus 4,000 pounds force multiplied by 5 feet. Okay. What am I missing here? Is there anything else? Well, the sum has to come to something, all right? Zero. Good. So plug that in your calculators, please. Let's find out what the moment at A comes out to.
I have negative 8,484.
Negative 8,484.
Yes.
Okay, that would be pounds force feet. Okay.
I got it to be positive.
Yeah, I was gonna say, it should be positive, shouldn't it? Because look, if we're summing moments about A, there's a lot more moment due to all this than there is at this force, with this force 10 feet out. At least that's what I would think, right? Because it just seems like it should come out that way. So what that really means is that the moment a day is actually, I was right. Now I'm getting confused. The moment a day is in this direction positive 8,484. Okay, so, yeah, that's what I would expect. Okay, so there are the reactions. Now, this is an interesting problem because you've never been able to do this before. You couldn't solve this kind of problem in statics. It's not possible, right? Because it's statically indeterminate. What did we do in order to solve this? Well, we used a piece of information that you actually could have used in statics, and that is the fact that this point can't deflect. But then we used deflection equations, which you didn't have in statics, that comes from strength of materials. Okay? Anyway, so what else are we supposed to do? We're supposed to draw shear and moment diagrams. I better not make the shear diagram too large or the moment diagram won't fit. So let's see, the general shape should still be what I came up with, it's just my numbers are off. And how does the shear begin? Well, the shear must begin at this value, right? Because if you imagine cutting the beam very close to the wall, there's essentially none of these other loads. And if there's a force of about 4,000 pounds on the beam trying to push it up, the shear must be pushing down with about that same amount. So that would be a positive shear. Let me put it here. And so it is measured in pounds force and starts out at 4,008.4 pounds force. Okay, so there's the first shear. Now, as we move along, foot by foot, 400 pounds is taken from this shear. Do you guys see that? Because this distributed load is pushing down on the segment of the beam, and so we don't have to have as much shear pushing down on the beam to keep it from accelerating. So at 3 feet times 400, that would be 1,200 pounds that we can take from, you know what, let's use another color. There we go. That way we can see it even though I write it in black. Okay, so now it all lines up nicely. So at this point, all we have to do is take 4,008.4 and subtract 1,200 from it, right? So we should get what, 2808.4? If I did that right? Okay. So there's the amount of shear in the beam. Then what happens? Well, we've arrived at the point load of 1,200 pounds. Excuse me. So we need to subtract another 1,200. In other words, this is going to step down to, let's see, I shouldn't go quite that far. I'll put the number over here. Well, 1,200 from this would be, what, 1608.4? Okay. Do you understand that the 1,200 pound drop here comes from the point load, and the 1,200 pound drop here comes from that 400 pound per foot load? Okay. So it's somewhat unfortunate the author of the problem made those two the same, but there it is. So anyway, if we continue then along 3 more feet, let's see, I'm going to run out of space here. 3 more feet, we're going to subtract another 1,200 pounds, so we're going to be down to 408.4. So let's see, 408.4. Sounds funny. I'm down to 408.4 pounds. Great success. Okay, so anyway, subtracting 800, the point load here, what would happen? Well, let's see, we'd go below the line and we'd end up at what? 393.6?
391.6.
391.6? Oh, yeah, okay. So negative 391.6 pounds force. Then 4 more feet at 400 pounds is minus 1,600. So let's see, we'd come down to just what we want to do. So negative 1991.6 pounds. So there we go. So there's the shear diagram. Now we need to make the moment diagram from it. The moment begins at 8484. So let's think about this for a minute. Is this a positive or a negative moment? Think about it this way. Here's a little segment of the beam. There's a moment at A like this. What kind of moment would we have to apply to resist it? Well, one like this. Is that a positive or a negative moment? That's a negative moment. Okay. So we have to begin at a negative 8484, and the units are pounds force feet. Okay? I thought it was positive. What happened? just a sign convention. That's all this negative is here, is just the sign convention. Okay, so we're going to start at, shouldn't have put a dot there, negative 84 foot-pounds. Okay? So now we need to add this area in order to find out where we come up to. The easiest way to do that is to take 4008.4 plus 2808.4 divided by 2 and multiply by 3 feet. Okay, to calculate this area. If I had a calculator, I'd do it with you. Actually, wait a second, I've got a whole computer right here. Okay, so let's see, 4008, 4 plus 2808.4 divided by 2 gives me the average height of this area, multiplied then by 3 feet, is 10,225.2. So basically this is positive area that's going to bring us up by 10,225.2. So if I subtract 84 from it, then we'll end up at somewhere here. And the number there, the change from here to here is the 10,255.2, whatever it was. It comes out to 1741.2. Okay, that's the moment at this point. Okay, so what's next? Well, next we want to add this area. Now let me ask you a question. This point here, I'm going to pull another line off of it, something like this. Is this a continuous line or no? How many people want to guess yes? It's a yes at this point. How many people want to guess no? Okay, why? Why do you think? Well, remember, this graph up here represents the slope. So the slope on this side is high, the slope on this side is lower. So there is a discontinuity here. Does that make sense? I can't draw it very well, but this should come off at a lower slope than this one entered at. It should be broken down like that, basically. Okay? So anyway, we could read off the slope. It's right here. The slope on this side is 2808.4. The slope on this side is 1608.4. Okay. So anyway, let's add up this area and see how much our moment changes. It's going to continue to increase because that's positive area. So what would we be? 1608.4 plus 408.4 divided by 2 multiplied by 3 feet. Okay, so 1608.4 plus 408.4 divided by 2 times 3 is 3,025.2. So that's what we need to add to 1741.2 to figure out the value of the moment at this point. Okay. When I did that, I came up with 4766.4, the moment. And hopefully this area is 4766.4, right? That's our hope. So we need 391.6 plus 1991.6 divided by 2 multiplied by 4 feet to calculate that area. So let's see. 391.6 plus 1991.6 divided by 2 times 4. Sure enough, it's 4766.4. So we come back. Now, of course, my drawing's not very good. It's not to scale, but let me ask you a question. Is this point continuous or not? What do you think? No, because there's two different slopes, right? On either side of the point. Okay, so there's discontinuity here and here in our moment diagram. Now the highest, or the largest moment occurs here. The largest shear also happens to occur at the left end of the beam. So at the wall connections where our largest shear and bending moment will occur. Okay. Let's see, was there anything else we were supposed to find? I think that's it. Any questions? Comments? Let me look at the problem statement quickly and see if they wanted anything else. We're supposed to indicate the maximum shearing force and bending moment in the beam, so there it is. Okay.